Welcome to the 10th lecture in general topology. The topics that we'll explore in this lecture include additional properties of postsets and simply ordered sets, and the properties of the order topology. Okay, so we'll start with some exercises from the previous lecture. So let the set A be the set which contains the integers 2, 4, 5, 10, 12, 20, and 25. Then the posset formed from the set A together with the relation less than or equal to has one maximal element, which is also the greatest element, namely 25, and the posset formed from the set A together with the relation divides has three maximal elements, namely 12, 20, and 25, but no greatest element. So proof: for the posset A with the relation less than or equal to, we have one long chain. 2 is less than or equal to 4, which is less than or equal to 5, which is less than or equal to 10, which is less than or equal to 12, which is less than or equal to 20, which is less than or equal to 25. So notice that there does not exist an element x which is distinct from the number 25 in the set A, such that 25 is less than or equal to x. And so the number 25 is a maximal element. Further, for every element y in the set A, we have that y is less than or equal to 25. And so the number 25 is the greatest element. So for the posset consisting of the set A with the relation less than, once again we will form the Hasse diagram. 2 divides 4, which in turn divides 12. 2 also divides 10, which in turn divides 20. 5 divides 10, which in turn divides 20. And finally, 5 divides 25. So notice that there is no element that 12 divides other than itself. There is no element that 20 divides other than itself. And there is no number that 25 divides other than itself. And so there does not exist an element x which is distinct from the number 12 in the set A, such that 12 divides x. There does not exist an element x which is distinct from the number 20 in the set A, such that 20 divides x. And there does not exist an element x which is distinct from the number 25 in the set A, such that 25 divides x. And so the numbers 12, 20, and 25 are maximal elements. Now there does not exist a element or an element x in the set A, such that for every element y in the set A, we have that y divides x, and so there does not exist a greatest element. Okay, so next, as a lemma, we will show that the greatest element is unique when it exists. So let the set X together with the relation R be a postset. The greatest element is unique when it exists. So proof. Suppose that X and Y are both greatest elements then, as the element X is a greatest element, it is also a maximal element and so there does not exist an element Y distinct from the element X in the set X such that X is related to Y, and hence if X is related to Y, then necessarily Y is equal to X. So as the element Y is a greatest element, we have that X is related to Y for every choice of X in the underlying set X, and so Y is equal to X. Okay, so the extrema that we have looked at so far, when they exist, occur in the given underlying set. So now we look at extrema that occur in supersets of a given subset. So let the set Y be a subset of the postset consisting of the set X with the relation R if there exists an element X in the superset X such that for every element Y in the set Y, we have that Y is related to X, then the element X is called an upper bound of the set Y, and the set Y is said to be bounded above So notice that if this element exists in the superset, then it does not necessarily occur in the set Y. That is, it is not necessarily an element of the set Y. But if there exists an element in the in a larger superset of the set Y, such that for every element Y, that element is related to the given element X, then that element is called an upper bound, and the set is said to be bounded above. So if the set Y is bounded above, then the element U in the set X is called a least upper bound, or the least upper bound, or supremum, the supremum of the set Y, if this element U is an upper bound of the set Y, such that U is related to Z whenever the element Z is also an upper bound. Of the set Y. So notice that the supremum of the set Y, which is denoted sup Y, is the least element with respect to the relation R in the set of all upper bounds of the set Y. That is, the supremum of the set Y is the least element in the set of all upper bounds. That is the smallest of all upper bounds. So it is an upper bound that is smaller than all other upper bounds. Further, if the supremum of the set Y is itself an element in the set Y, then the supremum of Y is the greatest element in the set Y. And if the set Y is not bounded above, we write the supremum of Y is positive infinity. Okay, so let's look at an example. Again, let the set Y, or correction, let the set A be the set of integers 2, 4, 5, 10, 12, 20, and 25 as a subset of the postset consisting of the positive integers with the relation less than or equal to. The supremum of the set A is 25, and as a subset of the set of positive integers with the relation divides, the supremum of the set A is 300. So proof. So considering the set A as a subset of the positive integers with the relation less than or equal to, notice that the set U, consisting of all positive integers, such that element x is greater than or equal to 25, is the set of all upper bounds of the set A. since for any of these elements, any element in the set A is less than or equal to an element in the set U. The least element in the set U is 25, and so the supremum of the set A is 25. And notice that this is an element in the set A and is indeed the greatest element in the set A. Now for the set A as a subset of the positive integers with the relation divides, notice that the product P, being the product of all the elements in the set A, the product 2 times 4 times 5 times 10 times 12 times 20 times 25 is a positive integer and is an upper bound of the set A, since this is a number for which it is divisible by every element in the set A. Now, from number theory, we know that the least integer that is divisible by all the elements in a given set of positive integers is called the least common multiple. And so the supremum of the set A is the least common multiple of the set A. And so we compute the least common multiple. We begin by looking at the prime factorization of the elements in the set A. So 2 is the prime number 2 to the power of 1. 4 is the prime number 2 to the power of 2. 5 is the prime number 5 to the power of 1. 10 is the prime number 2 times the prime number 5. 12 is the prime number 2 to the power of 2 times 3. 20 is the prime number 2 to the power of 2 times 5. And finally, 25 is the prime number 5 squared. So the least common multiple of all these elements in the set A will contain as multiples all of the primes that occur as the factors of the given elements in the set A to the highest power that it occurs in any one of the factors. And so the prime number 2 occurs in some of the factors, and the highest power is 2. The prime number 3 also occurs, and in any of the factors, the highest power of that prime number is 1. And finally, the prime number 5 occurs, and the highest power of its occurrence is 2. So we have that the least common multiple of the elements in the set A is 2 squared times 3 times 5 squared, which is 300. And so the supremum of the set A is the least common multiple, which is 300. So if we were to describe the set of all upper bounds of the set A as a subset of the positive integers with the relation divides, we would describe that set as all positive integer multiples of the number 300. Okay, so new definition. Again, let the set Y be a subset of the Postset consisting of the set X with the relation R if there exists an element X in the superset X such that for every element Y in the set Y, X is related to Y, then the element X is called a lower bound of the set Y, and the set Y is said to be bounded below. Again, notice that this element need not necessarily be in the set Y. if this element exists in a larger subset, then that element is called a lower bound, and the set Y is bounded below.